Good day, everybody. How are you all doing? Today, we are going to talk about energy analysis of closed systems. So, here I go. And so, here we are talking about conservation of energy, first law of thermodynamics. So, we are talking about a closed system. Work energy can be thought of energy expended to lift a weight. A closed system moving relative to a reference plane, which is the horizontal line, is shown below, where z is the elevation of the center of the mass above the reference plane. So z is the elevation and v is the velocity. V bar is the velocity of the center of mass. For closed system shown above, conservation of energy principle, or the first law of thermodynamics, is expressed as so change in energy of the system, which is delta E, is E in minus E out. According to classical thermodynamics, we consider the energy added to the net heat transfer to be the net heat transfer to closed system, and the energy leaving the system to be work done by the closed system. So Q net, energy added to the net heat energy to the closed system, energy added to be net heat transfer to the closed system, that is Q net, and energy leaving the closed system. So Q net is coming in, U net is leaving out. It is the net work done by the closed system, and the change in energy is Q net minus W net. Therefore, Q net is equal to Q in minus Q out. Okay. Q net is, of course, the net energy coming in is Q in minus Q out. And W net is W out minus W in plus WB. What is WB? Is the work done by the system, is going from state 1 to state 2, pressure multiplied by change in volume. Normally, the stored energy or total energy of a system is expressed as the sum of three separate energies. The total energy of the system, E system, is given as, okay, so it is given over here. Recall that U is the sum of the energy content within the molecules of the system other than kinetic and potential energies of the system as a whole, and is called the internal energy. The internal energy U is dependent on the state of the system, okay, and the mass of the system. For a system moving relative to a reference plane, the kinetic energy Ke and the potential energy is given by. So kinetic energy is, of course, we know mass times velocity. That arrow indicates that a direction is a vector quantity, mass multiplied by velocity squared divided by 2. Potential energy, of course, is the mass times gravitational constant multiplied by the change in height. So the change in stored energy of the system is delta E, is change in internal energy plus change in kinetic energy plus change in potential energy. But what is change in energy? Note from the conservation of energy, the first law of thermodynamics for closed system. Change in energy is Q net coming in minus the work done by the system. W net is change in internal energy plus change in kinetic energy plus change in potential energy. What does this say? That energy is conserved. It is going from one form to another. Nothing is lost. So Q net minus W net is the change in internal energy. We will find that this is the most commonly used form of the first law. Since a thermodynamic cycle is composed of processes that cause the working fluid to undergo a series of state changes through a series of processes such that the final and initial stages are identical, the change in the internal energy of working fluid is zero. Why? Because it comes back to its original state. The first law for a closed system can be written as first law for a closed system operating in a thermodynamics cycle where change in internal energy is zero because it comes back to its original state because it is a closed system. So Q net is equal to W net. That means total energy coming in is equal to total work done by the system. And that is what is shown in the picture. So compare complete the table given below for a closed system undergoing a circle. 1 to 2, okay, is net energy coming in is plus 5. So U2 minus U1 is minus 5. 2 to 3 is plus 20. And 3 to 1 is minus 5 for Q net in kilojoules. Work net between 2 and 3 is plus 10. Okay. So here is in this next section, we will look at the boundary work in detail. The piston cylinders of an internal combustion engine shown below may be considered to operate as a closed system when intake and exhaust valves are closed. This is the IC engine, is an 8-piston cylinder device. Boundary work. Work is the energy expended when a force acts through a displacement. Boundary work occurs because the mass of the substance content within the system boundary causes a force, the pressure times the surface area, to act on the boundary surface and make it move. Hence, the piston is moving. That is what happens when products of combustion, the gas in the figure below, of an internal combustion engine contained in a piston cylinder device expands against the piston and forces to the piston. Okay. Forces the piston to move. So that is what happens when the products of combustion, the gas in the figure below, which is in pink color, moves up, okay, of an internal combustion engine contained in a piston cylinder device expands against the piston. It's expanding against the moving up and forces the piston to move. Thus, boundary work is done by the gas on the piston. Why it is boundary work? Because it's done at the boundary of the external, I mean, as the outer, as the boundary, top boundary of the gas. Note the gas could also be real fluid such as steam or refrigerant. Okay. And total boundary work is equal to change in from position 1 to 2 integration of delta change in work boundary, which is position 1 to 2 F times ds. And F times ds can be written as F divided by A multiplied by A ds. Why do we do that? Because F by A is pressure, force divided by area, and A times ds is volume. So boundary work is pressure times the change in volume. Since the work is process independent, the differential in the boundary work, delta WB, is process dependent. Since the work is process dependent, it depends on the process. The boundary work delta WB is written as PdV, where dV is the change in volume that depends on the process, is called inexact. The above equation for WB is valid for quasi-equilibrium process and gives the maximum work done during expansion and the minimum work input during compression. In an expansion process, the boundary work must overcome friction, push the atmospheric air out of the way, and rotate a crankshaft. So WB is W friction plus W atmosphere plus W crank. Okay. And that is obtained by integration force of friction plus pressure times atmosphere multiplied by area plus F crank multiplied by ds. Okay. Okay. So here we are doing an integral. Okay, we integrate the boundary work can be performed for each process. We need to determine P as a function of volume. So look at the way it is done. Process path is from 1 to 2, shown by the pink arrow, and pressure is on the vertical axis, horizontal, and volume is on the horizontal axis. So as we work problems, we will be asking what is the pressure volume relationship of the process. Remember that this relation is really the force displacement function of the process. Okay, the boundary work is equal to area under the process curve plotted on the pressure volume curve. Okay. P is the absolute pressure and is always positive. When dV is positive, WB is positive. When dV is negative. When is dV positive? When we are pushing up. When dV is negative, we are compressing. WB is negative. Since the areas under the different process curves on a PV diagram are different, the boundary work for each process will be different. Next figure shows each of the process. Each process gives a different value for boundary work. Why are these WA, WB, and WC different? Because the area under the curves are different. Okay. PV diagram. Okay. So here they're showing in a machine. Okay. Boundary work required to drive a compressor. The figure below shows a 7.5 horsepower and two piston compressor with intercooling attached to an 80-gallon reservoir. Okay. The calculated boundary work W net to compress the gas will be negative because pistons do work on the air. When you compress the air, your volume change is negative. Okay, so it's a negative work. Of course, the actual work supplied by the motor W in is negative of the calculated work. So when it's a constant volume process, volume is held constant, dV is 0, and the boundary work equation becomes integration from path 1, position 1 to position 2, depend on the path taken, P times dV. But remember, the volume at position 1 is equal to the volume at position 2 because it's the same value on the horizontal axis. Hence, change in volume is 0, boundary work is 0 at constant volume. If the working fluid is an ideal gas, what will happen to the temperature of the gas during this constant volume process? Okay. Here the volume is changing from position 1 to position 2. So pressure, boundary work is pressure times change in volume, that is from V2 minus V1. For constant pressure process shown above, is the boundary work positive or negative? It's negative because we are going from a large value to a small value. The final value V2 is smaller than V1. Hence the boundary work is negative. We are compressing basically. If the temperature of an ideal gas is held constant, then the equation of state provides the pressure volume relationship. This is the ideal gas equation. So for pressure, you substitute M times RT. M is the molar mass divided by capital V, which is the molar volume times dV. So the boundary work is M times RT, which are constant, and natural logarithm V2 divided by V1. The above equation is the result of applying ideal gas assumption for the equation of state. For real gases undergoing an isothermal constant temperature process, the integration in the boundary work could be done numerically. Polytropic process in which pressure volume relationship is given as multiplied by V exponent n. So volume is exponent n. PV exponent n is constant. The exponent n may have any value from minus infinity to plus infinity depending on the process. Some of the more common values are given here. So constant pressure process n is 0. Constant volume process n is infinite. Isothermal and ideal gas B is 1. And adiabatic and ideal gas is, remember adiabatic no heat chain K is equal to Cp by Cv. Here K is the ratio of the specific heat at constant pressure to the heat at constant volume, Cv, specific heat at constant volume. Okay. So the specifics will be discussed later. The boundary work done during the polytropic process is found by substituting the pressure volume equation. The result is constant in the numerator divided by Vn for pressure dV. So you are integrating with respect to volume. So it is P2 V2 minus P1 V1 divided by 1 minus n when n is not equal to 1. And if n is equal to 1, then the relationship is PV ln V2 by V1. So note that for the polytropic process, the constant is P1 V1 is equal to P2 V2. As we know, it's equal to R, gas constant. Notice that the result we obtain for an ideal gas undergoing a polytropic process, undergoing the isothermal process. 3 kilograms of nitrogen gas at 27 degrees Celsius and 0.5 megapascal are compressed isothermally to a final 0.3 megapascal. Okay. In a piston cylinder device, determine the minimum work of compression in kilojoule. Nitrogen system, nitrogen content in a closed piston cylinder device process is constant temperature. So property relation, check the reduced temperature and pressure for nitrogen. The critical state properties are found in table A1. So TR1 is T1 divided by T critical. Okay. This is reduced temperature. Similarly, P reduced one is P1 divided by P critical. And PR2 is twice the PR1. Since PR is less equal to 1, which is 0.044 as shown, and T is greater than twice the critical because T reduced is 2.38. Nitrogen is an ideal gas because T is less than twice the T critical. And we use ideal gas equation of state as the property relation. We use PV equal to MRT. Plug it in the equation, find the work of compression. It's MRT ln V2 by V1. For an ideal gas closed system, mass is constant. M1 is equal to M2. So P1 V1 divided by R1 RT1 is equal to P2 V2 divided by RT2. Since P is R's cancel, we obtain the ideal gas equation. And the temperature is same. T2 is equal to T1. Okay. So we plug it in. Okay. Where do we plug it in? We plug it in the equation. Okay. We use the value of R is 0.2968 kilojoule per kilogram degree Kelvin. Okay, multiplied by the temperature, which is 300 Kelvin, multiplied by the mass of the gas, which is 3 kilogram. And then we take the natural logarithm of the two pressures. And that gives you net work. Okay. And it's negative. And per unit mass basis, you divide by the mass. The net work is negative because work is done on the system during the compression process. Thus, the work done on the system is 184.5 kilojoule or 184.5 kilojoule of work energy is required to compress the nitrogen. So water is placed in a piston cylinder device at 20 degrees Celsius and 0.1 megapascal. Weights are placed on the piston to maintain a constant force on the water as it is heated to 400 degrees centigrade. How much work does the water do on the piston? So we have to look at the property relation from steam tables. Process is a constant pressure process. And why do we look up to the steam table? Because we have to look at the volumes or the specific volumes from the steam table. So it is P V2 times P pressure times in parenthesis V2 minus V1 divided by mass. When you divide by mass, the capital V2 divided by M is small v2, which is specific volume at position 2 minus specific volume at position 1. Where do I get these figures? I get it from the steam table, okay, and plug it in, and then I calculate the boundary work. So this is positive, okay, we are expanding. That's why work is positive. Same, a similar problem, 1 kilogram of water is contained in a piston cylinder device at 100 degrees Celsius. The piston rests on a lower stops such that the volume occupied by water is 0.835 meter cubed. The cylinder is fitted with an upper set of stops. When the piston rests against the upper stops, the volume enclosed by the piston cylinder device is 0.841 meter cubed. Okay. A pressure of 200 kilopascal is required to support the piston. Heat is added to the water until the water exists as a saturated vapor. How much work does the water do on the piston? So here is the figure. Okay. Work calculation, we need the specific volumes. Okay. So specific volume works out as 0.835. Since VF, okay, is less than VG, VF is less than VG and V1, VF is less than V1, VF is less than V1, and V1 itself is less than VG, okay. State 1 is in the saturation region, so P1 is equal to 101.35 kPa. Show this state on a PV diagram. Now let's consider the process for the water to reach the final state, process 1 to 2. The volume stays constant until the pressure increases to 200 kPa. The piston will move. So the process 2, 3, the piston lifts from the bottom stops while the pressure stays constant. Does the piston hit the upper surface after reaching the vapor state? Let's set V3 is capital V3 divided by M, which is 0.841. Now at pressure 200 kPa, VF is the 0.001, VG is 0.88. Again, V3 is between VF and VG. Piston hits the upper stop before the water reaches saturated vapor state. Now you have to consider a third process, process 3 to 4. With the piston against the upper stop, the volume remains constant during the final heating to the saturated vapor state and the pressure increases. Because the volume is constant from in the process 3 to 4, V4 is equal to V3 is 0.841 meter cube per kg, and V4 is a saturated vapor state. Interpolating in either the saturation pressure table or the saturation table, temperature table at V4 equal to VG gives final pressure is 211.3 kilopascal, V4 equal to VG, T4 is 122 degrees centigrade or Celsius, and net work is going from 1 to 4 is actually from 1 to 2, 2 to 3, and then 3 to 4. Okay, 1 to 4, 1 to 2, no change in volume. 3 to 4, no change in volume. So it's 0. So the final work, net work is between from 2 to 3, okay, which is MP times V3 minus V2, okay, and works out to 1.2 kilojoule. So find the required heat transfer to example 4.4, review the solution procedure of example 4.4 and apply the first law to the process. First law, remember, is conservation of energy. EM minus E out is delta E, and Q net minus W net is the change in internal energy. In example 4.4, we found that net work is 1.2 kilojoule. So Q net is 1.4 is W net 1.4, which we know 1.2 plus delta U. So we have to calculate delta U1 to 4, which is M times U4 minus U1. Those are specific internal energy. At state 1, T1 is 100 degrees centigrade, V1 comes from the table. So V fluid is between V1 and VG at T1. The quality at state, you have to calculate. Remember, X is the quality of that mixture of steam and water. Okay, and X works out to 0.499. Why do we know that? Need that because that's the X. We need to know the quality because that way we can calculate the internal energy at state 1, which is U1 is equal to U fluid. F means fluid plus x1 times UFG, which is the difference between the specific internal energy between fluid state and gaseous state, comes from the steam table. Okay. Because state 4 is a saturated vapor state and V4 is 0.841 millimeter cube per kg, interpolating in either the saturation pressure table or saturation temperature table at V4 equal to Vg gives U4. So this comes from the table. Hence, delta U14 can be calculated as mass times the change in internal energy, and the net heat transfer is W net 14 plus change in internal energy U4, delta U14. So this amount of heat is added to the water. So air undergoes a constant pressure cooling process in which temperature decreases by 100 degrees Celsius. What is the magnitude and direction of work for this process? So it is going from state 1 to state 2 as shown in the picture diagram between P and V, PV diagram. Property relation, ideal gas law, PV equal to RT, process is constant pressure. So work calculation network is 0 plus W B12 boundary work for 1 to 2, which is pressure times V2 minus V1, which is MR times T2 minus T1. The work per unit mass is divided by M. Divide by M, and we get the specific work. And if we want to determine the required heat transfer through this process, we apply the first law as Q net minus W net is equal to WU, is equal to delta U, change in internal energy. Internal energy change of the air, we now investigate how to find the internal energy change of an ideal gas. Before the first law of thermodynamics can be applied to system, ways to calculate the change in internal energy of the substance enclosed by the system boundary must be determined. For real substances like water, the property tables are used to find the internal energy change. For ideal gases, internal energy is found by knowing the specific heats. Physics defines the amount of energy needed to raise the temperature of a mass of substance 1 degree as the specific heat at constant volume for a constant volume process, and the specific heat at constant pressure Cp for a constant pressure process. Recall that enthalpy is the sum of the internal energy and the pressure volume product. So, Cp is the change in internal energy with respect to temperature delta U by delta T at a constant volume. Cp is the change in internal energy Cv, and Cp is the change in enthalpy dH by delta T. Simple substances, the thermodynamic state of a simple homogeneous substance is specified by giving any two independent intensive property. Let's consider the internal energy to be a function of T and V. T temperature, absolute temperature, V is specific volume, and H is a function of temperature and pressure. Total differential du is delta U by delta T with us at constant volume times dt plus delta U plus delta divided by delta B at constant temperature times dV. So now we know delta U by delta T at constant volume is Cv, and delta U by delta Vt is not known, is kept at that. Okay. So dH similarly can be written as Cp dt plus delta H by delta P. Change in enthalpy with respect to pressure at constant temperature times dP. Using thermodynamic relation theory, we could evaluate the remaining partial derivatives of U and H in terms of the functions P, V, and T. These functions depend upon the equation of state for the substance. Given the specific heat data and the equation of state for the substance, we can develop the properties tables such as the steam tables. For ideal gases, we use thermodynamic function theory of chapter 12 and the equation of state PV equal to RT to show that U, H, internal energy, enthalpy, specific heat at constant volume, and specific heat at constant pressure are functions of temperature alone. Okay. For example, when total differential U is equal to U is a function of temperature and specific volume, internal energy, the function theory of chapter 12 shows that this. So delta U by delta V at constant temperature is T times delta P with respect to temperature at constant volume minus P. P is equal to RT by V, hence delta P by delta T is R over V at constant volume, and delta U with respect to delta volume at temperature, constant temperature T. We plug it in, T times R divided by V minus V, which is P minus P, is 0. Okay, so for ideal gases, CV is specific heat at constant volume is a function of temperature, and change in internal energy with respect to specific volume at constant temperature is 0. And CP, specific heat at constant pressure, is CP only function of temperature, and delta H, change in internal enthalpy with respect to pressure at constant temperature, equal to 0. So the ideal gas specific heats are written in terms of ordinary differential. Because it's a function of only one variable, instead of writing partial derivatives, we write ordinary differentials. So Cv is du by dt for ideal gas, and Cp is dH by dt. That means Cv is the change in internal energy with respect to temperature for ideal gas, and Cp is the change in enthalpy with respect to temperature for ideal gas. So here is the process. Okay. Figure shows the smaller specific heats vary with temperature for selected ideal gas. Okay. Translation mode, it is 5 by 2 RU. And then rotation modes. Okay, let me see. Rotation mode is 7 over 2 RV, and vibration mode is 9 over 2 R2. Okay. And the differentials in internal energy and enthalpy for ideal gases become du is equal to Cv dt, dH is equal to Cp dt. Okay, so here they're finding the change in internal energy from state 1 to state 2, H2 minus H1, which is nothing but change. Remember, Cp is constant, the specific heat at constant pressure times change in temperature. Okay, so they're looking at three different processes: constant volume, pressure is A plus BV linear relationship, and process 1 to 2C, that is constant pressure. Why is constant pressure? Because it's a horizontal line. Whereas the first one is constant volume because it's a vertical line. And they go through all of this. Okay. So they show you what is the best way to determine the specific volume, specific heat at constant volume and the specific heat at constant pressure by doing this integration and so forth. Okay. And then they calculate the change in enthalpy. Okay. For the case. Okay. Definition of delta U and delta H for ideal gases, just um, consider the enthalpy for now. Change in enthalpy is H2 minus H1, which is Cpt is a constant, specific heat at constant pressure, function of temperature dt. So let's perform the integral relative to a reference state where H is equal to H reference and T is equal to T reference. So actually they're breaking it into two parts. First part, you're going from T1 to T reference. Second part, you're going from T reference to T2. Okay, so delta H is actually going from T reference to T2 minus. Why the second item is minus? Because you've changed the limits of integration. Previously, it was from T1 to T reference. T1 is a lower to T ref. Now you made going from T reference to T1. You've changed the limits of integration, hence it is negative. So this is what it is. So delta H is H2 minus H reference minus H1 minus H reference. Or H is equal to H reference plus integration from T reference to temperature. Cp is a function of T, specific heat at constant pressure with respect to temperature. And for internal energy, U is equal to U reference, is going from T reference to T. These two relations form the basis of air tables on a mass basis and other ideal gas tables. Okay. Okay. So we are going from state 1 to state 2. Actual path is shown. The approximation is shown by the dashed line. Determine the average specific heat for the air at 305 degrees Celsius. And the answer is given. So using the definition of enthalpy, H is equal to U plus PV, and writing the differential of enthalpy, the relationship between specific heats and ideal gas is this, or dH is equal to du plus dRT, or Cp dt for dH, for du write Cv dt plus R dt. So Cp is equal to Cv plus R. And the specific heat ratio K is equal to Cp over Cv. Okay. So here is a problem. 2 kilograms of air are heated from 300 to 500 Kelvin. Find the change in enthalpy by assuming empirical specific heat data from table A to C, air tables, specific heat at average temperature, and use 300 Kelvin. So there are three processes. So table A to C gives the molar specific heat at constant pressure, Cp. Notice it is capital Cp. So this is 20. So this is an expression is T. Molar, so kilojoule per kilogram mole. Enthalpy change per unit mole, you write the formula out, integrate, do the integration correctly, and you can get change in internal energy, specific internal energy. I mean, change in specific internal energy. That is kilojoule per kilogram. That you divide by the molecular weight of air, kilogram per kilogram. So the molecular weight of this gas is 28.97 kilogram per kilomole. Why do you divide by the molecular weight? Then the enthalpy change will be in kilojoule per kilogram. Okay, and then you multiply by the mass of the gas, total mass, to get the total change in enthalpy. Okay, and then you plug it in. So there are three different processes and three different kinds of work. Yeah, I mean, change in internal energy, you are seeing the first one was 407.98 kilojoule. Part B is come close, 405.66. And what about part C? Constant, constant specific heat at average temperature. So what is it coming out to? That's also coming close to. The net change in enthalpy is coming close, 405.2, and part D is also coming close. So everything is close depending on which process you use. When we apply a methodical solution procedure, thermodynamics problems are relatively easy to solve. Each thermodynamics problem is approached the same way as shown in the following, which is a modification of the procedure given in the textbook. Sketch the system, show the energy interactions across the boundaries, determine the property relation, is the working substance an ideal gas or a real gas, begin to set up and fill in the property table, determine the process and sketch the process diagram, continue to fill in the property table, apply conservation of mass and conservation of energy principles, bring in other information from the problem statement, called the physical constant, such as the volume doubles or pressure is halved during the process. Develop, develop enough equations for the unknowns and solved. So here is a situation, nitrogen gas, we have the system boundary, nitrogen in the tank, property relation, nitrogen is an ideal gas. The ideal gas property relations apply. Let's assume constant specific heats. You are encouraged to do using variable. So we are going from uh, position 1 to position 2. First, the constant volume process going from 1 to 2. Okay, so conservation of mass, because it's a closed system, M2 is equal to M1. Plug it in. P2 divided by P1 is 1.333. First law of closed system. We get Q net minus W net is delta U for nitrogen undergoing a constant process. Volume process dV is 0. So net work is 0. Okay. Ideal gas relation W net is 0. First law becomes constant specific heats is M times CV, constant volume T2 minus T1. MCV times that is the Q net, and specific heat Q net is net heat transfer per unit mass divided by mass. Another one, air is expanded from 100 degrees Celsius from zero point 0.4 megapascal to 0.1. Pressure is decreased, air expands. Okay. It's a piston cylinder device, closed system, constant temperature. So, property relation is PV, MRT, and delta U is CV times T2 minus T1. Conservation of energy. Also, we apply, and Q net minus W net is equal to delta U. That is total heat transfer minus total work done is equal to change in internal energy to a closed system. And we calculate the work from 1 to 2. And we find the relationship between V2 and V1. And then we calculate the change in internal energy, delta U12, from which we can calculate the change in specific heat, okay, which is, change in net heat or change in specific net heat, which is Q net divided by mass, okay. And some more energy relationship, internal energy and enthalpy changes of solids and liquids. Cp is equal to C. We treat solids and liquids as incompressible substances. That is, we assume the density or specific volume of the substance is essentially constant during a process. We can show that the specific heats of incompressible substances, such as chapter 11, are identical. Cp is equal to Cv is equal to C. So change in internal energy becomes C times dt, where C is the constant specific heat. And we plug it in. So change in internal energy for incompressible energy, delta V dV is 0. dH is equal to du plus pdv plus vdp. Change in volume is 0. So dH is du plus vdp. Integrating change in internal energy is change in internal energy delta U plus V delta P. What is delta U? C times delta T. Multiplied by V delta P, or H solid, delta H solid is delta U solid plus V0 times delta P. And for delta H solid, V0 is 0. So delta U solid. So delta H solid is equal to delta U solid, which is C delta T. Specific volume is approximately 0 for solids. Okay. Constant pressure process, delta H liquid is equal to delta U liquid is C delta T. Constant temperature process, delta H liquid is V delta P. And properties are given. Okay. 2-liter volume about beverage has just been removed from the trunk of your car. Temperature of the beverage is 35 Celsius, and you always drink the beverage as 10 degrees Celsius. How much heat energy must be removed from your 2 liters of beverage? You are part A, part B, you are having a party and need to cool 10 of these 2-liter bottles in 1/2 hour. What rate of heat removal in kilowatt is required? Assuming that your refrigerator can accomplish this and that electricity costs 10 cents per kilowatt hour, how much it will cost to cool these 10 bottles? The liquid is in the constant volume closed system uh, closed system container. Okay. So Q net is the heat removed. Process is constant volume. V2 is equal to V1. Conservation of mass, because mass remains constant. So mass is capital V divided by total volume divided by specific volume. we used in conservation of energy for a closed system. Okay. And network is W net other plus WB. The only energy crossing the boundary is the heat transfer, leaving the container, assuming the container to be stationary. The conservation of energy becomes minus Q out is equal to the heat leaving the system is the change in internal energy, which is M times C times delta T. Okay. So the heat rate transfer to cool the 10 bottles in 1/2 hour is specific heat that we have to take it out times you convert it into kilowatts and then multiply it by the unit cost of electricity. Okay, that's it for today. I will stop here today. If you have any question or comment, write me a comment. I'll get back to you as soon as possible. If you like this video, please give me a thumbs up. If you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button and let YouTube know that you would like to be notified every time I upload a new video. How do you do that? Hit on the bell. Click on the bell. Okay. And please come back tomorrow. Do not forget to watch me tomorrow when I'll discuss another interesting topic. Thanks for watching. Take care. Have a nice day. And please subscribe to my channel. I have all kinds of YouTube videos. So take a look at my channel, subscribe to my channel, then you can download these videos free. Thanks for watching. Take care. Have a nice day.